Hello, this is Class 06, Calculus 3. Vector-valued function. A vector-valued function, also referred to as a vector function, is a mathematical function of one or more variable whose range is a set of multi-dimensional vectors or infinite-dimensional vectors. Now the output is not just a single scalar or constant. Now output of a function is a vector. The input of a vector-valued function could be a scalar, just number, or a vector. A common example of a vector-valued function is one that depends on a single real number, like parameter t, often representing time, producing a vector vt as a result. In terms of the standard unit vector ijk of Cartesian three-dimensional space, these specific type of vector-valued functions are given by expressions such as, here ijk are just unit vectors such as I is 1, 0, 0. Okay, so ijk, let me write down. So in the three-dimensional space I, so we have I and j and k. Here I is basically 1, 0, 0, and j is basically 0, 1, 0, and k is basically 1, 0, 0, 1. Alright? Okay. So RT is FTI ZTJ, or RT is FTI ZTJ HK. So RT here it is like a vector of FT, GT, HT, where FT, GT, HT are like a coordinate function of the parameter t. Therefore, you can regard RT as a movement of some particle on the plane. RT, this one, is a movement of some particle in three-dimensional space. The vector RT has its tail at the origin and its head at the coordinate evaluated by the function. This is example, a graph of the vector values function RT. Here, ft, you can look at this one. ft is 2 cosine t, and the gt here is 4 sine t. So 2 cosine t, 4 sine t, and t, ht is this t, indicating a range of solution and the vector where evaluated near t equal 19.5. Here, 19.5. The vector shown in the graph to the right, this one, is the evaluation of function near t equals 19.5 between 6 pi and 6.5 pi, i.e. somewhere more than 3 rotations. Okay, 2 rotation, 2 pi is 1 rotation, 2 pi is 1 rotation, 4 pi is a second rotation, 6 pi is 3 rotations, so it is between 6 pi and 6.5 pi, it is more than 3 rotations. The spiral is the path traced by the tip of the vector as t increases from 0 through 8 pi. Now, vector function can also be referred to in a different notation. So we write this one as this one, and we write this one as this one. So RT is the vector FTGT. Second RT is a vector FTGT HT. It is vector valued function. Now in vector valued function, we have very important concept called the Jacobian matrix and Jacobian determinant. In vector calculus, the Jacobian matrix or Jacobian matrix or Jacobian matrix. Anyway, the Jacobian matrix is the matrix of all first order partial derivatives, okay? Or first order partial derivatives of a vector valued function. When the matrix, the square matrix, both matrix and determinant are referred to as a Jacobian in the literature. So Jacobian can mean sometimes a matrix, or Jacobian means sometimes the determinant of the matrix. Now let's take a look at. Suppose f is a function from n-dimensional space to m-dimensional space. Suppose f Rn to Rm is a function which takes as input the vector x in n-dimensional space and produces output the vector fx in Rm m-dimensional space. Then the Jacobian matrix J of f, Jf, is an m row n column matrix, m by n matrix, usually defined and arranged as follows. So J is partial of f with x1, and then to the partial of f, partial xn. Here, input f is the vector valued function. So because f is a vector value, so this one is each column, so this piece is this one. So f is a vector value in m-dimensional space. F has value in m-dimensional space, so it has element of f1 to fm. And this is first one, so we take derivative with the first one. And second one would be delta f2 to, and then each one delta f1 to delta f, partial f1 to partial fm, and then we take derivative all with respect to x2. And the last line is again partial f1 to partial fm, and then we take all with respect to derivative with respect to xn. Now, so the i's row and j's entry, the element in i's row and j's column would be look like this. Jij, we write as Jij. So it is a Jij is i's row and j's column of Jacobian matrix would be partial fi. Okay, i's function in the vector valued function, and take partial derivative with respect to j's argument. Now this matrix whose entries are function of x, now they are also we just take derivative, so we can evaluate all those functions in the particular value of x. So in Jacobian matrix is entry in the Jacobian matrix are all function of x. This matrix whose entries are function of x is also denoted by df, jf, or delta f1 to fm and partial f1 to fm over partial x1 to xn. Note that some literature define Jacobian as the transpose of the matrix given above. Sometimes some book or literature change row and column. Now, in the Jacobian matrix, it is the like a linear approximation. So Jacobian matrix is used as a linear approximation. So if P is a point in Rn, f is differentiable at P, then its derivative is given by JFP. Oh, so this Jacobian matrix is like generalized version of gradient. You know, gradient is generalized version of first derivative. So, and the Jacobian is generalized version of derivative. Gradient. Jacobian is generalized version of gradient. So, Jacobian is most general. Out of three, Jacobian most general first derivative. Anyway, in this case, the linear approximation described by JFP is the best linear approximation of f near point P in the sense that this one. So this is error term. For x close to P and where small o is the real O notation for x equals x compared to P, and then x minus P is the distance between x and P. So you can regard, simply speaking, you can regard this one right as error, which converges to 0 when x goes to P. So it is like a 0 when x and P is close enough. Now compare this to a Taylor series for scalar function or scalar argument, truncated first order. So it's a first order Taylor series expansion. So first of the Taylor series expansion is fx equals fp plus f prime px minus p, and the second order, third order, and we all regard it as like small number. If x is close to p, they are small number. So this is error. So in a sense, both gradient and Jacobian are first derivative. The former gradient, the first derivative of a scalar function of several variables. The latter Jacobian are first derivative of a vector function of several variables. Now you can understand the step-by-step generalization. So let me write down again. So for example, so let's start from Taylor series expansion again. So as you know, Taylor series expansion is like f x equals to f a plus f prime a x minus a plus error term. So small o, this one goes to 0 when x is close to a enough. When x close to a, this one converts to 0 very quickly. And then so it is the single valued function. And then for f, now x is a factor, full factor. Because it's confusing, let's put arrow over here to denote this factor. Full factor, then it is f a. Now a should be a vector as well. Plus now, well, we need a kind of version of first derivative for vector function. Whose element vector? So then we have del gradient. So f a, and then transpose x minus a. Actually, I'm wrong. It is not transpose. It is just element by element. Element by element. Sorry, it should be like, it is like element by, it is not, so it is vector, so like element by element operation. And then here, O, so we need a 2. Because now it is the distance between the two vectors. So it's distance between two vectors, so I put 2 on to norm basically. Now function itself, f is also vector. Now f is vector, f is a vector valued, and x is also vector valued. Right? Then we put a like this, plus now we need a Jacobian. Now let's write this on thicker, like Jacobian. Here Jacobian of f a, and then x minus a. Oh, sorry. Here we need. They are all vectors, right? They are vector. This is vector. This is vector. This is vector. Plus now error term. Right? So they are all first order Taylor approximation. Okay, they are all first Taylor, or it is in other words, they are called linearization. As I told you, the famous linearization is Campbell-Schiller linearization. So the first one is the single valued and then single variable. Single variable. Now second one is single valued. Function is single valued f. Single valued f, but multiple multivariable. Now the third one is multi-valued f, and then multi-variable. Okay, so this one. Single valued and single variable, single valued multiple variable, and then multi-valued multiple variable function in f. So here, yeah, this is the first derivative, and then this is a gradient. The third one is a Jacobian. Gradient, and then first derivative. Okay. And then let's go to next page, and let's please check the example of Jacobian matrix determinant. Click. Now examples. Now multi-valued function. Consider a function from R to R2. So plane to plane given by its multi-value. So f is a vector. fxy is x square y, 5x, and sine y. So clearly it is a multi-variable, multi-valued function. Multi-variable means equals multi-variable function because we have two variables x, y. It is multi-valued because it has value 2. First value is vector, 2 vector, this value, this value. Then we have, let's write f1 xy as the first element in the vector valued function, first function. And then second function in the vector valued function, as we write that as f2 xy, this one. Then the Jacobian is in the first one. This one is we take derivative of f1, f2 with respect to x. In the second column, we take derivative of functions, both functions with respect to y. So f1x is 2xy, and then f2x is 5, and f1y is what is f1y? Yeah, f1y is x squared, and f2y sine y is cosine y. So we have this one. And the Jacobian determinant, if you take the determinant, then this one minus this one. So 2xy cosine y minus 5y squared. Now, next one, polar Cartesian transformation. Now, the transformation from polar coordinate r psi to Cartesian coordinate xy is given by the function f r plus. R plus means this one, r plus is basically positive area from 0 to 2 pi to r square, because it is a polar coordinate. So it moves from 0 to 2 pi, right? From 0 to 2 pi in one circle to r square with a component such that x is r cosine phi and y is r sine phi, right? So basically, if you draw the graph of this one, right? So I think you learned in high school, but here, so x equal r cosine phi, y is r sine pi over here, right? So basically, right, this is the xy, xy. Then we can express s1. This is the length of r. Then y is basically cosine. Let's write down this one as a green one. Okay. So r is basically this point is cosine of r. This is the y, and this one would be the r. Now sine height, so r sine. Right. So if we have the length r and then angle, we can transform that into the x y into the we can change the coordinate. Right. So it is a transformation from polar coordinate to the Cartesian coordinate. Now let's calculate Jacobian. Well, it is again this is a multi-valued and multivariate function. Multivariate because it has two values. This function has two values x, y, and multivariate because it has two variables r and pi. So j r pi is first function, and then second function. This line is first function, second function, and this is the first argument, second argument. So the first column is take derivative of both functions with r. Second column is take derivative of both functions with pi. So xr is, if we take derivative of r, then we have only this term, r goes away this term. So this is same to this one without r. Now next line we take derivative of this one. So cosine phi, take derivative minus sine phi derivative cosine phi. So this one. Okay. So in some sense, the Jacobian determinant is equal to r. If we take determinants, this one minus this one, so determinant r. Okay. This can be used to transform integration between the two coordinate systems, like this one. Now, spherical Cartesian transformation. Now it's a transformation for the spherical coordinate. What is spherical coordinate? Yes, spherical coordinate this one. Yes, so first, L, and then we have two angles. First angle is this one, this plane, phi, and second plane is from the top, go on, theta. So this is called spherical coordination system. So here x is r sine theta, cosine phi. Okay, so this term is same to this one. Okay, but now we have to add, we have to move the vertical direction. So r sine theta cosine phi, y is r sine theta cosine phi, and these are cosine theta because it is height. Okay, it is height. The Jacobian matrix, now it is a multivariate function because it is multivariate because this function takes the value of x, y, z, and it is multivariate because the variable is r theta phi. So Jacobian is the first column we take derivative with r. So this one without r. Second column we take derivative theta. So r cosine theta cosine phi, again cosine theta sine, and then for the cosine theta take derivative minus sine. And then the last one we take derivative with phi, and then third one of course is 0 because there is no argument about phi, and then minus sine, take derivative of this one, minus sine, take derivative plus cosine. So we have this line. The determinant of this matrix, if you take determinant, it is r squared sine theta. Now, it is another example. Now, Jacobian matrix function f from R3, R4. Now, 3 variable and then vector is 4. Vector value, the multivariate function again. So, this function takes 4 values, y1, y2, y3, y4. And y1 is x1, y2 is 5x3, y3 is 4x2 squared minus 2x3, y4 is x3 sine x1. Now if you calculate Jacobian, then first line take derivative of all x1. Second line take derivative of all function with x2. Third line take derivative all with x3. We have this one. So if we calculate this one, they are partial. If you compute them, we have this one. Now it is R3 to R3. the Jacobian determinant. Now it requires calculating Jacobian determinant. Okay, so we have to calculate determinant. So y1 equals 5x2, y2, 4x1 square minus 2 sine x2, x3, y3 is this one. So the first line, take derivative of x1, so it is 0, there is no x1, it is 0, it's 8x1. Now second line, second column, we take derivative x2, so it is 5. Take x2, okay, the sine, so we need to use chain rule. So sine derivative becomes cosine, so minus 2, but chain rule, so we take derivative x2, so x3 comes out, so minus 2x3 cosine x2, x3. Now third line, third column, we take derivative with x3, so first one, no x3, so it is 0. Second one is again chain rule, so again, minus 2 cosine, and then x2, x2, and chain rule, we take derivative of x2, x3, with x3 to x2 comes out, so minus 2x2 cosine x2, x3. And then if we take derivative, we compute the determinant of this 3 by 3 matrix, then it becomes this one. And then there are other good examples. Now next, dot product. Dot product is a very interesting concept. So what is a dot product? Dot product. So let's discuss algebraic definition of a dot product. The dot product of two vectors. Okay, so in order to calculate dot product, we need two vectors. So suppose we have two vectors with the same length or same number of entry. So A is a vector made up of A1 to AN. And then B is a vector B1 to Bn. It's defined as AB. It is the AI, BI from I to N. So A1, B1 plus A to B2 plus dot, dot, dot plus A and Bn. Where sigma is denotes the summation notation and n is the dimension of vector space. So it's dimension. For example, in three-dimensional space, 1, 3, minus 5, dot product 4, minus 2, minus 1 is 1, 4, 3, minus 2, minus 5, minus 1, which is 4, minus 6, 5, which is 3. Okay. Actually, in Excel, let me show you the example. So Excel. Let's start Excel. So suppose that we have two vectors here, two vectors A and B. So vector A is, let's say, 2, 3, 4. Vector B is, let's say, minus 1, minus 2, 3, and 10. Okay. So in order to calculate A dot B dot product, then we have to do multiply element by element, this one by this one, and then copy and paste this one. So yeah, this one is minus 2, minus 1, minus 2, 3, minus 3, minus 2, 4, 10, 40. So we have to add them all, sum. Yeah. So 29 is A dot B. 29 is A dot B. In Excel, actually, it is another way. It's called the sum product. In Excel, we have a function called sum product. So sum product is first. We select this one and this one, and then enter the same number. So basically, it means a dot operation is a sum product in Excel. We do the product first. Product, element by element product, and sum across product. So it is sum product. Dot element is sum product. By using matrix multiplication, and if we treat vector as 1 by n matrix, which is a column vector, the dot product can also be written as a vector. Their vector A dot B is A, B. Now B is transpose. Here B transpose means transpose of V. Now using the above example, 1 by 3 matrix, row vector is multiplied by 3 by 1 matrix, column vector to get result. 1, 3, 5, 4 minus 2, 1, 3. So this one, 3. So again, in Excel is sum product. Now, for dot product, we have actually more important definition of dot product, which is geometric definition. Geometric definition. In Euclidean space, a Euclidean vector is geometrical object that possesses both a magnitude and a direction. Okay, so magnitude and direction. So if we use this example here, so suppose this is the point 2, 3. Well, we can regard this as this is x, this is y. Then here Euclidean vector. If we input Euclidean vector, Euclidean vector is a geometric object with both magnitude and direction. So magnitude is the distance from 0 to this one, and the direction is this one. So we have arrow. So magnitude is length of this one, and direction is the direction of arrow. So Euclidean vector has length and direction. Okay, let's remind that. So in Euclidean space, a Euclidean vector is a geometrical object that possesses both a magnitude and a direction. A vector can be pictured as an arrow. Its magnitude is its length, and its direction is the direction that the arrow points. Okay, so here magnitude is length. This is the magnitude, and the direction is where the arrow points. This is the direction. Yeah, this is the direction of this vector. This is the direction. Okay. The magnitude of a vector A is denoted by norm A. We read norm A. So it is the distance of A, magnitude of A. Now the dot product of two Euclidean vector AB is defined by A dot B's length of A multiplied length of B, and the cosine of theta. Cosine of theta, where theta is the angle between AB. Well, in the previous case, I defined AB as a sum product. Now I define A dot B like this way. Now you can prove it, but this one are always same. They are always same. You can easily prove it. They are all same. So you can interpret A dot B this way or A dot B this way. They are mathematically equivalent. Well, but if we write A dot B in the geometrical way, this way, it is more interesting. In particular, if A and B are orthogonal means that A and B are, the angle between A and B is 90 degrees. Then the angle between them is 90 degrees. So theta is 90 degrees. Cosine theta, 90 degrees, which is the half of pi. It's 0, right? Cosine 90 degrees is 0. So A dot B cosine 90 degrees is 0. So when A and B are orthogonal, now we have an interesting result there. When A and B are orthogonal, they are 0. So here, when orthogonal, like this one, suppose we have this one. This is A, this is B, then A dot B is 0, right? Because cosine of 90 degrees is 0. Second, this implies that dot product of A with itself. Now A and A. So A dot A is A and cosine 0. Right? Cosine 0 is 1, so it is A square. Right? A square. A square. Which gives, so A is a root of AA. Right? So therefore A dot A. Very interesting result, right? The formula for Euclidean length. So it's a formula for Euclidean length of the vector. Now, intuitively, dot product indicates extent that two vectors are similar direction. Or intuitively, dot product indicates how much vectors move together. Or it indicates the product of length of direction in the length of vectors in same direction. Length of vectors in same direction. So let me show you what it means. Okay, so suppose A dot B. A dot B is norm A, norm B multiplied by cosine theta. So suppose this is A. Let me change the color. Let me say this one, this color. So let's say this is A, and let's say this is the, no, this is should be straight. This is straight, not straight. Well, again, let me say it this way. Okay, this is much better. Let's say this is B. Okay, and then A, B. Okay, so let's write this one is now it becomes B multiplied by A cosine theta. Now A cosine theta, so it is a theta. So A cosine theta is basically this one. The length of this one. So this line. This line is basically now A, okay, it is perpendicular. So this is A cosine theta. Of course, this is the length, A cosine theta. So, and then the length of this one, the length of B is B. So basically, this means that we are multiplying. Therefore, what we are just doing is we are multiplying length of this line, right? Basically, we are multiplying length of this piece and length of this piece. Okay. So, well, if they are orthogonal, in this case, 1 is 0. So, when we have this way, AB, then A dot B is now here A cosine theta is 0, right? A cosine theta is 0. B and then A cosine theta, where theta is 190 degrees, so this piece is 0. So it is basically point, so it is 0. So basically it means when they are orthogonal is 0. And suppose they are more than 100, more than 90 degree. Okay, now it is theta. Now we have the length of this one. This is the, right, like this one. So now the length of this line is now this is the A cosine theta, but now it is less than 0, and this is B, right? B dot B. Now they are, so this A dot B is less than 0. So in a sense, dot product means that how much two arrows point to similar direction. In this case, it is positive. It is positive because they are casually in the same direction. It is 0 because they are orthogonal. It is negative. This one is negative because it is basically the opposite direction. So in this case, basically A does not help B at all, right? B want to move this way, but A move this way. So basically A does not help B at all. In this case, basically A is like doesn't helping is A does not help B. Actually, A is prevent B from moving this direction. So that's why it's negative. They are not helping each other. A and B, they are not helping, so it is negative. When in this case, A and B, they help each other, although it is not perfect, they seems to help each other, so it is 5. If the theta is 0, they help each other perfectly, right? Perfectly. So therefore, inner product measure how much two arrow help each other. Magnitude of how much two arrow, two power help each other to the same direction. So let's read the intuition again. That's why dot product indicates the extent that two vectors are in the similar direction, or how many vectors move together, how much vectors help each other, or it indicates, dot product indicates the product of lengths of vectors in the same direction. Okay, lengths multiply lengths of two vectors, and then we transform that the same direction. That's the intuition of dot product. Thank you.